Our second learning target for the chemical reactions unit is applying the law of conservation of mass in order to balance chemical equations. And before we start switching around coefficients, we have to know some basics first. The first is that a balanced chemical equation shows the types of substances in the chemical reaction and the amount of those substances. And in order for a chemical equation to be balanced properly, the chemical formulas of the reactants and products must be written correctly. So for the most part, we'll give you the chemical formulas of your reactants and your products, but we will ask you to change around the coefficients or how much of those things you have. So naturally, we use numbers to balance out those substances, and those numbers are put in front of the symbols and formulas, and those are called coefficients. The law of conservation of mass is what we've been talking about a lot in the past few days, and it applies perfectly to balancing chemical equations because the number of atoms of each element on the reactant side, or what we start with, must be and will be equal to the number of atoms of each element on the reactants on the product side. So what we end with. And there are two key rules for balancing chemical equations. The first is that you will never ever change the chemical formula, which means you'll never mess with the subscripts, because those are what we have and what we'll end with, and we'll give you those. What you will change, you'll only change those front numbers or the coefficients, because that shows how many molecules of each substance are involved in a chemical reaction. So even though we can't change what we have, we can change how much of it we have. So let's work through balancing a chemical equation together. And we're going to break this up by step, and we won't do this for anyone else but this first one, so just bear with all these simple steps. The first step is to determine the number of atoms for each element on both the reactant and the product side. We're basically doing an atom count. So if I look at my reactant side, I see that I have 2 irons and 3 oxygens. So that's what I start with. But it looks as if I end with 1 iron and 2 oxygens. That's my initial atom count for the product side. Now obviously these are not the same numbers, so this equation is not balanced. In order to figure out which element to start with, we're going to find the least common multiple. And we should have learned that in math, and the least common multiple is the smallest number each element will have in common by multiplication. So basically, we're going to multiply. And we're going to multiply the number of atoms on the reactant side by the number of atoms on the product side. So for iron, we have 2 atoms on the reactant times the 1 atom on the product, and that equals 2. For oxygen, we have 3 atoms on the reactant side multiplied by the 2 atoms on the product side, and that equals 6. After you're done with the multiplication, you're going to select the element with the largest least common multiple. So in this case, if I compare 2 to 6, the largest least common multiple is 6. This means that I need to get 6 atoms of oxygen on each side of the equation. After I realize that I need to get 6 atoms of oxygen on each side of this equation, my next step is to determine the coefficient, or the number of molecules, in order to achieve that. But first, I'm going to pull down my initial atom count, and I'm actually going to do it twice. I'm going to do it down here as well, and you'll see where this is going. Alright, so we're going to start with oxygen because that was our largest least common multiple. So in one molecule of Fe2O3, I have 3 atoms of oxygen. But if I want to get to 6, I can say, okay, well, if one molecule gets me 3 atoms of oxygen, then 2 molecules will get me to 6, because if I have 2 molecules of 3 atoms each, I'll get to 6 atoms of oxygen. However, because it's bonded to iron, we also have to do 2 times 2. So we also have 4 atoms of iron now on the left. Now it's really unbalanced. But let's keep focusing on oxygen. So if one molecule of O2 has 2 atoms of oxygen, that means I would need 3 molecules of O2 because 3 times 2 gets me 6 atoms of oxygen. So now I have the same number of atoms of oxygen on the left and the right side. So O is balanced. So we're good to go on that particular element. Alright, so I'm going to pull down what I have here. So I already said I had 2 molecules of Fe2O3 and 3 molecules of O2, and I'm also going to adjust my atom counts for what I already have. So it should match what we have up there right now. So oxygen is already balanced, so now we need to balance iron. So if I have 4 atoms of iron on the left, that means I need 4 atoms of iron on the right. So because iron has a subscript of 1, the easiest thing to do is just to put a 4 here, because 4 times 1 gets me 4 atoms of iron. So now iron is balanced. So our 2 different elements are balanced. That means our equation is fully balanced and we can move on. Let's do some guided practice problems together. And now we're going to take away those step-by-step pieces and put it all together. Now, first up is always an atom count. So on the reactant side, I have 1 atom of zinc and 2 atoms of oxygen. While on the right side, or the product side, I have 1 atom of zinc and 1 atom of oxygen. The next step is to do least common multiples so I know which element to start with. So I have 1 atom of zinc on the left times 1 atom of zinc on the right, and that's 1. While for oxygen, I have 2 atoms of oxygen on the left times the 1 atom of oxygen on the right, and that equals 2. The question you have to ask yourself is which element has the largest least common multiple? And the answer is oxygen. And then how many atoms should that element have on each side? That's the answer to our least common multiples problem. That would be 2. So we're going to try to get 2 oxygens on each side to start. If we look at the reactant side, we already have 2 atoms of oxygen, so we're not going to mess with that. But on the right side, I only have 1. Now you might be thinking, why can't you just put a 2 here and be done? Because you can't change the subscripts, so don't write that down. If you need 2 atoms of oxygen, we actually have to put a 2 in front of this whole thing, because we can only add the molecules that we have written down. So if zinc oxide has 1 zinc bonded to 1 oxygen, I'm going to need 2 sets of them in order to get my 2 oxygen atoms. But I also need to remember that it affects the zinc too, so now I have 2 zinc atoms. Well, now my oxygens are balanced, but my zinc is not. Luckily for us, on the reactant side, zinc is a singular atom. So if I need 2 of them, because now I have 2 zincs on the product side, I can just put a 2 in front of zinc, and now my equation is balanced. If you don't feel comfortable leaving this blank, you can put a 1 here. If you feel confident and want to try this independently, pause the video, and then you can check your answers by pressing play. If you don't feel comfortable doing this independently, stick around and we'll do this one together. My first step is to always do the atom count. So on my reactant side, I have 1 boron and 2 fluorines. On my product side, I have 1 boron and 3 fluorines. Step 2 is to do the least common multiples. So I have 1 atom of boron on the left times 1 atom of boron on the right, and that's 1. But I have 2 atoms of fluorine on the left times 3 atoms of fluorine on the right, and that equals 6. So if I compare these 2 numbers, obviously 6 is bigger, so fluorine has the largest least common multiple, and our goal is to get 6 atoms of fluorine on each side. So if I look at my reactants and 1 molecule of fluorine is F2, so it's 2 atoms of fluorine, that means I need 3 molecules of fluorine. So 3 times 2 gets me 6 atoms of fluorine, which is what our goal was according to our least common multiple. And if I want to get 6 atoms of fluorine on my product side, I need to have 2 molecules of BF3 because 2 times 3 gets me 6 atoms of fluorine. But because these 3 fluorines are connected to 1 boron, Now I have 2 boron atoms total on the right-hand side. So now that my fluorines are balanced, but my borons are not. So I have 2 borons on the right-hand side, but I need 2 over here. And because boron is a single element, we can put a 2 here, because 2 times 1 is 2. Let's do another one. Again, if you feel comfortable doing this independently, please go on and then press play when you want to review. Or if you still don't feel comfortable, stick around and we'll do this last one together as well. So the first step is an atom count. So I have 2 atoms of nitrogen, because N2, and 2 atoms of hydrogen. While on the flip side, I have 1 atom of nitrogen and 3 atoms of hydrogen. Then step 2 is to do least common multiples. So I have 2 atoms of nitrogen on the left times 1 atom of nitrogen on the right, and that equals 2. Hydrogen is 2 on the left. We're going to multiply by the 3 it has on the right, and that equals 6. Which element has the largest least common multiple? If you said hydrogen, you're correct. And our goal is to get 6 hydrogen atoms on each side, because that's the answer we got from the least common multiple. So if we look at this particular hydrogen molecule, we'll see that 1 molecule of this has 2 hydrogen atoms. So in order to get to 6, I would need 3 molecules of H2, because 3 times 2 is 6. On this side, we have 1 N connected to 3 H's. So if 1 molecule of NH3 has 3 hydrogen atoms, that means I need 2 of them to get a total of 6 hydrogen atoms total. So that's 6. But these 3 hydrogen atoms are connected to a nitrogen. So now I have 2 times 1 nitrogen atoms. So if I look, my hydrogens are balanced and my nitrogens are balanced. And again, if you're not comfortable with leaving this blank, you can put a 1 here.